Okay. All right. Good morning, all. Good morning, all. And welcome to another lecture in the EXTATIC series. Jerry Sullivan asked me to give this sometime last week, and I wasn't quite sure what was the title. I think the title EUV photo absorption, but I didn't know nearly enough about EUV photo absorption to talk about it for an hour and a half. So I've retitled it EUV metrology, and it's going to be an introductory lecture to light sources, to EUV light sources and their role in metrology. And I think Larissa at 11 o'clock will go into more detail on some of the items here. So the overview is in the metrology systems that we're developing with EUV light sources, typically we're trying to view something small, and typically we're trying to use an EUV light source to do it. The light source can be a discharge system that's driven by an electrical current, or it can be a laser system, or it can be a combination of both. And the system that we're going to be investigating in the PhD program with Garum is going to be a combination of the two. And in the talk today, I'm going to talk about the light source and collection of photons from the light source. I'm going to talk a little bit about radiance and brightness from the light source. And I'm going to talk about how that relates to illumination of a sample in a metrology system. And first of all, I'm just going to try and put that into some kind of a context as to where it fits into an imaging system in general. So you've seen enough pictures of small things over the last few days, I suppose, but we're in a world where people want to see smaller and smaller items, whether it be biologists wanting to unpick the molecular nature of what's going on in life, to semiconductor manufacturers wanting to be able to optimize their production processes and be able to see down at the nanometer scales that they're printing at. And we don't have complete vision into the small world. We have some techniques, which I'll go into now in a second. And the motivation really behind EUV metrology and efforts in that development are to try and give us another window, into the small world. So techniques that exist at the moment, there are many scanning techniques and scanning probe techniques like AFM and SLAM. But I'll leave them alone for the moment, and I'll just talk about a few electron microscopy and visible microscopy imaging systems and how they relate to the EUV efforts that we're making. So scanning electron microscopy. In scanning electron microscopy, you have an electron beam that's condensed or focused through electron lenses onto a sample, and it's focused onto a fine spot. And at that fine spot of interaction, the electrons interact with the surface, and the high energy electrons produce secondary electrons by cascade processes on the surface of the material. And you have an electron detector over to one side of your sample, and the electron detector detects these cascade electrons. And the orientation of the surface with respect to the detector is what really gives you the contrast in scanning electron microscopy. You can get some fantastic images of creatures at a very small scale. I think the field here was some few microns. So this is a worm from a hot vent somewhere. So it looks like something alien. And it actually is. But anyway, wonderful pictures. The depth of field is enormous, and that's why you can get pictures like this. And the resolution you can get down to about 1 nanometer. Sample preparation is relatively simple, so it's a good technique, but it doesn't give you very much by way of chemical resolution, and it's slow. Well, it's not that slow. It's slow at high resolutions. Moving on to imaging techniques, if you look at transmission electron microscopy, again takes a source of electrons, but this time it uses that source of electrons to illuminate an object field on your sample. And the transmission through your sample of this of this electron illumination is what gives you your image through an objective and projection lenses in the transmission electron microscope. And the resolution from TEMs can be enormous, but the disadvantage for somebody trying to image is that you have to have an extremely thin sample, and that sample has to have high contrast. And normally that contrast is driven by absorption, and for that you need high Z elements typically for the high energy electrons that give you the high resolution. So for a biologist, for example, they have to use osmium or gold staining in their samples, and they have to make their samples extremely thin. And this isn't something that allows itself, and this that allows ready application of TEM and high resolutions to biology. And for semiconductor sampling, it's similar. You can't look at bulk samples with TEM. Photo emission electron microscopy is another imaging system, and one a little bit more relevant to what I'm going to talk about today. It's got a resolution that's similar to SEM if you have an aberration corrected system, but it involves focusing photons onto a sample and using electron optics to focus the photo electrons that are produced in this region here. It images the photoelectrons that are produced in this region here through an objective and projection lenses onto a camera. And the magnifications, like I said, that you can get are very high. You can get resolutions down to about a couple of nanometers, and you'll see that has an effect because of fixed camera size and the object field here. And so you have to illuminate a very small area with your photons, and I'll get to that in a second, or in a short while, and you'll see what relevance that has to the sources that we try to develop for UV metrology. So we require a photon source here, even though it's an electron microscopy technique. In soft X-ray imaging directly, you have systems like Hans Hertz microscope, where he uses a laser plasma soft X-ray source, a laser plasma water window soft X-ray source, and he focuses that using a multi-layer collector onto a sample and illuminates the sample, and then uses a zone plate objective to image his object onto a CCD. I think the resolutions he has at the moment are down to about 20 nanometers, and the advantage of this system here is that he's able to use the contrast mechanism, the natural contrast mechanism of the absorption difference between water, or oxygen mainly, and protein or carbon in the biological samples. So biological samples are made up of water and proteins. The proteins are heavily carbonated, and the water is heavily oxygenated. So you've seen this before, I'm sure, in some of the slides that people have given. But this water window region allows for 10 micron thick samples of hydrated or water-containing materials to be imaged. So again, he needs a photon source for this. And the requirements for the photon source again here, his field of view here, his object field of view is somewhere around 5 microns to give him the resolution that he wants. In EUV mask metrology, again, there's a source requirement. In the lithography process, they use an EUV light source to illuminate a mask, and that mask has a pattern on it, and the pattern on the mask is projected onto a silicon wafer. And the semiconductor manufacturers would like to know that the pattern on the mask is what they want it to be, so they need some way of imaging the mask to test it before and during processing times. So they require an EUV microscope to look at the surface of the mask and to inspect it as well. And they need, in the production process, they take the mask and they reduce it by a factor of 4 onto the silicon wafer to produce smaller features. But in the process of trying to inspect the mask, they need to magnify the mask features by a factor of about 750. So they need a very high magnification here as well, and they need a source that will allow them to give a resolution of about 40 nanometers. And the key for them is high throughput, and that means fast scanning and being able to inspect quickly. They need a light source that will enable them to do that as well. So the challenge in all of this, and in all of these efforts, is to take objects with nanometric features and micro object fields, and to image them up onto micron-sized pixels and macro image fields. So the magnification process there is common to pretty much all of the imaging techniques that I talked about. And just to briefly run over Nyquist again, in terms of the camera, for a rough hand-waving number of pixels that you would require to resolve a pattern of a particular spatial frequency, your pixels would need to have twice the spatial frequency approximately according to Nyquist, so that the signal coming from the pixels, when modulated by the pattern being projected onto the pixels, will give you a variation in your signal which should hopefully match your original pattern. If you reduce the frequency of your pixels and you apply the same mask, you get no contrast. So that's hand waving and rough, but you need to have more pixels. You need to have at least twice the frequency, theoretically, in order to give you a resolution that you require. So what does that roughly mean for somebody using a CCD and an EUV light source to image something? Well, just forgetting the light source for a second and just considering magnification. If you have a CCD with 13 micron pixels and you apply the Nyquist criteria, you see that the 13 micron pixels on the camera at 1000 magnification correspond to 13 nanometer pixels of the object. And the minimum resolvable feature will be twice the pitch of the minimum resolvable feature will be twice the pitch divided by the magnification. So in this case here, about 40 nanometers is the best you're going to do from 13 micron pixels at 1000 magnification. And that has a large impact on your object field of view. Your object field is driven by the resolution that you require, and driven by the magnification that you require to get there onto a detector of particular size and particular pixel size. So detectors are normally much less than 50 by 50 millimeters. If you need magnification of 1000 to see 40 nanometer features, then your field of view is going to be much less than 50 microns. So in most of the imaging techniques that I was talking about there, the field of view is extremely small, and you need to couple a light source onto that extremely small field of view in order to image it. Just briefly as well to mention another aspect of the light source that's important in highly resolving systems, in the resolution of this system here, the spatial resolution of this system here is largely driven by the numerical aperture of the objective. So if you want a high resolution, you need a high numerical aperture on your imaging system if you're using photons to image. That numerical aperture on your objective is important, but you also need to match that numerical aperture by the illumination numerical aperture as well. So if you underfill your objective, you're going to reduce your resolution as well. So that's something we have to be conscious of too. We can't just apply illumination at any numerical aperture. So a brief summary of all of that is that tiny objects need to have a tiny illumination field when you're using a macro-sized detector, and we need to match our illumination solid angle, or illumination numerical aperture onto our imaging system as well. And there are two microscopy limitations of soft X-ray light sources that we look at a little bit more now. So, a quick question. The quick question is, if the eye can theoretically resolve 6.5 micron features, what are the raw dimensions likely to be? So, without knowing anything else. Without knowing anything else, if the retina can resolve 6.5 micrometer features, what are the size of the detectors on the retina.
At least more than 6.5.
More than 6.5?
No, sorry, less. So it should be less than 6.5 to
Yeah.
yeah,
So
6.5
it's the Nyquist limit, yeah. So that's just ballpark as well. Larissa is going to go into more detail later on, and the answers are much more complicated than that. But if you want to go into ballpark numbers, that's approximately what it is. So the cones or the rods in the eye are approximately 3 microns in diameter, something like that. They may not be. A biologist will probably correct you there. For the purposes of what we're talking about here, it's fine. Anyway, I'll talk a little bit more about soft X-ray sources now. So that was just a little bit of context. I suppose this is just a little bit more context, but it's context on sources themselves rather than the general imaging systems. And EUV light sources exist in all sorts of flavors and in all sorts of radiances. And we'll talk a little bit more about radiance later on as well. But the ones that we're going to be most interested in are light sources that are incoherent, and they would typically have a maximum radiance or maximum brightness, which is significantly less than synchrotrons and maybe 12 orders of magnitude lower than FELs. The general region of brightness covered by the sources that I'm going to talk about is higher than micro discharge or micro focus X-ray sources and lower than synchrotrons. That's approximately the region that we're in. The incoherent sources that I'm going to talk about and that are applicable to the metrology, the EUV metrology systems that I'm going to talk about are discharge plasmas and laser plasmas. Discharge plasmas are produced by applying high current across electrodes with a medium in the gap, and the medium is ionized and produces a discharge, and typically in the systems that we use for EUV, the current is sufficiently high to cause magnetic contraction of the plasma, and plasma contracts to be a small, dense emitter, small, highly ionized, dense emitter of EUV photons. And these sources are typically greater than a few hundred microns in size, and they can be up to tens of kilowatts. Laser plasmas are typically on a scale which is a lot smaller. You can make laser plasmas, EUV emitting laser plasmas, maybe not 10 microns, but we've certainly made them 15 or 20. And they can be powered up to tens of kilowatts as well. So the size of the source is important. I'm going to talk about the size of the source now. Well, first of all, I'll briefly mention what the sources are. The sources are highly ionized plasmas, and within these highly ionized plasmas, the excited states that are in the high temperature, highly ionized plasmas give you various types of transitions, which give you EUV emission. The plasma emission is typically dominated by bound transitions between electrons from two bound states, and you also have recombination radiation, which is a radiation from free state into a bound state, from emission from a free state into a bound state, and Bremsstrahlung radiation, which is emission from free electrons from free transitions. And typically the spectrum is dominated by bound transitions, and when you go to higher Zs and when you go to open F and D shells, you can get very, very large numbers of transitions occurring in very close proximity to each other, nearly degenerately, and these very large arrays of transitions can appear as broad, bright emission on the spectrum. So this picture here is a picture of wavelength in this direction here, taken from a photographic plate from a spectrometer in UCD. And these features here are individual lines from the laser plasma, and this here is an unresolved transition array, a broad emission feature from one of the plasmas. The laser plasmas themselves produce radiation in different spectral regions depending on the temperature of the plasma, and the temperature of the plasma is driven by the power density of the laser focused onto a surface. If you're focused onto a surface or onto a liquid, it's driven by the power density and the wavelength of the laser. So they're the two levers that you can pull when trying to increase or decrease the electron temperature of the plasma. So you can change the spectral characteristics of the laser plasma by changing the wavelength or changing the power density. And typically for emission around 13.5 nanometers with tin, we would have an electron temperature of somewhere around 40 eV would be a typical electron temperature there. The electron density of the plasma is important as well in terms of laser coupling and in terms of opacity. So the critical density for a plasma where it won't absorb laser radiation further is approximately 10 to the 21 over lambda squared per centimeter cubed. And this means that for a CO2 laser at 10, which is a 10 micron wavelength, it emits, or it has a critical density of around 10 to the 19 per centimeter cubed, and a YAG laser emitting at 1 micron has a critical density of around 10 to the 21 per centimeter cubed. Why is that important for sources? Because EUV light is absorbed quite effectively in plasmas at a density of 10 to the 21 per centimeter cubed, and less effectively. It's more transparent. You can produce more transparent plasmas at 10 to the 19. So that's another feature in laser plasmas. Just to mention briefly what are the main large plasma sources being developed currently. This is a source being developed close to Larissa's university, and it's based on a technique that is similar to what's in the system that Giron is going to use during his PhD. The idea is a laser triggered vacuum arc is the type of discharge. You have a high voltage across two electrodes, and both electrodes are metal electrodes coated with a liquid metal. And the reason that they do that is because the triggering process involves ablating some material from the surface of the electrode, so you need the electrode to be regenerative. And there's a huge amount of heat involved here as well, with tens of kilowatts going into the system. But a laser is focused onto the liquid surface that's on the rotating electrode, and some ionized material is ablated into the gap between the electrodes. There's a high voltage across the electrodes, and this high voltage drives a current, and the current is sufficiently large to produce a pinch, which gives you emission in the soft X-ray in the EUV region, and the emission volume is somewhere around a millimeter in diameter, something like that. So I think Philips have EUV power coming from a system like this of around 300 watts at the moment, 300 watts into 2 pi, so they're extremely powerful systems. Cymer and Gigaphoton, I haven't got any more detail on it than this because they're quite secretive about what they do, but they use a normal incidence reflector and a laser plasma driven by a CO2 laser to produce their light source. So that's the two competing light source types for EUV lithography, for very high power EUV lithography. These aren't really relevant to metrology systems, but they're just what's out there at the moment. The light source currently being used mostly for EUV metrology is an energetic light source which produces about 10 watts of EUV power at 13.5 nanometers, something like that. And that's an electrodeless Z-pinch discharge system as well. So there are no laser plasma systems currently being used in metrology, I don't think. So just to talk briefly about brightness. Brightness and radiance are the same thing, and it refers to the power density from a light source or from a cross-sectional area when viewed by an observer through a solid angle omega, and the radiance in this case is given by this equation here, which tells us that approximately the brightness of a source is the power of the source over the area of the source over the emission solid angle of the source, which is 2 pi. So most of the sources that we're looking at are incoherent sources that are emitting, well, 4 pi. But yeah, we normally talk about brightness in terms of 2 pi. So when brightness numbers, okay, yeah, no, we talk about power in 2 pi, but we talk about brightness, and the brightness here refers to 4 pi, of course. Yeah, it does. So our emission numbers that we talk about, our power emission numbers, are normally power into 2 pi steradians. So if we were quoting our power numbers correctly into 4 pi steradians, then this would be power over 4 pi. In any case, if you can see from this here that if you've got a source with a tenth of the diameter and the same power, then it's got 100 times the radiance. So going back to metrology and sources for metrology, typical laser plasma or typical discharge plasmas, like I said, have a diameter or have dimensions of around 350 microns or bigger. And the systems that are currently used in metrology have a power of about 10 watts. If you had a 20 micron laser plasma, you could produce the same radiance from the plasma with a 30 milliwatt source. So you can see that if radiance is the driving force in your imaging system, that using a much smaller plasma allows you to produce that same radiance with much less input power. So that's more or less it about sources for the moment. And just source collection is the next thing that I wanted to talk about there. Are various methods deployed in source collection. And the simplest one is to use, because EUV photons are reflected very poorly in normal incidence by most materials, the simplest way to collect EUV photons is by grazing incidence reflection on an ellipsoidal mirror. So you take an ellipsoidal section. You take an ellipsoidal section here like this, and you put your plasma at one focus, and you get focusing. You get a focus beam on the other side. It's not imaging. You can get an imaging grazing incidence system by having 2 reflections and using a hyperbolic section in front of an ellipsoidal section. But each section captures a smaller solid angle, so you need to make it nested in order to collect sufficient photons from a system like this. And then the simplest, but the simplest in terms of collection solid angle, but the most difficult in terms of manufacture, is a normal incidence system where a multi-layer mirror can be used in front of a plasma to collect a high solid angle and focus the EUV from your plasma to somewhere useful. The collection issues that currently exist for EUV systems involving imaging, you need to have many mirrors, you need to have illumination optics that take the light from the source to the sample, and you need to have projection optics that take the light from the sample to a wafer or to an imaging system. And these multiple reflections of at most 70% each can take your total power reflected from one mirror is about 70%, and from 11 mirrors is somewhere around 2%. So the throughput of light through an imaging system in EUV is very small. So that's an issue. The optics themselves typically reflect extremely well in the infrared and invisible as well. So this is a problem. And debris, 5 nanometers of tin debris, will reduce the reflectivity of these mirrors by 50%, and roughening of a couple of nanometers on one of these mirrors will reduce the reflectivity of the mirror by somewhere around 90%. So these are the collection issues that exist with EUV light sources. And they're common to metrology sources and to lithography sources. The collection efficiency, which is important, for power transfer through the system. Collection efficiency depends on what solid angle that you collect. If you have a grazing incidence collector, for example, that collects 5 degrees between 20 and 25 degrees, you can see that the angle that the solid angle that subtends is given approximately by this, and by this area here. And if you were to take the same 5 degrees and collect at a higher angle, at between 50 and 55 degrees or somewhere around that the total flux of photons through that particular solid angle is much higher. The relationship between solid angle and collection angles is given by this. So it's preferable to collect photons at a higher angle if possible. That's why normal incidence reflectors are so much more effective than grazing incidence ones in terms of collection solid angle. Reflectivity is another issue, and reflectivity in grazing incidence optics tends to drop off rather quickly with angle of incidence. So in order to calculate approximately what your total reflectivity through a system with a particular solid angle is, the solid angle increases as your collection solid angle increases. So that gives you more collection solid angle, but your reflectivity is decreasing at the same time. So your total reflectivity through the system is weighted by the reflectivity of your grazing optic as well. So there is some balance and some optimum there. You can't, with a grazing incidence system, you can't just collect more light. With a normal incidence system, you can collect 2 pi. You can collect over half of the radiation from the source with a reflectivity of about 70%. So the throughput from a normal incidence system is very high, and the throughput from a grazing incidence system will be significantly lower because the collection solid angle available is lower and the reflectivity is typically lower as well. And just to mention as well that from a radiance point of view, the solid angle doesn't make any difference because solid angle is in the denominator of the radiance calculation anyway. But reflectivity does affect radiance transfer through the system. If you have a reflectivity of 70% here, it means that your radiance drops by 30% at least between your source and your image point. Typical grazing incidence mirrors that are used currently, ruthenium mirrors are used because in very high power sources where high power transfer is required, because the reflectivity is quite high, out to about 30 degrees. So these are manufactured by Media Lario, and they were being made by Carl Zeiss as well. But they're not really practical for metrology sources because they're too expensive and they require protection. For metrology sources and for other systems, you can use gold-coated grazing incidence optics, and the reflectivity is lower, but they're simpler to manufacture, and they can be more disposable. So if the metrology optics are damaged, they can be replaced. In UCD, we're working on a technique at the moment as well to develop liquid-coated grazing incidence optics, and these optics are coated with the same metal that's in the plasma in the first place. So the plasmas that we use to produce 13.5 nanometer radiation are typically tin containing or tin alloys, and we can use those tin alloys to coat the inside of an optic. And the alloys can have reasonably high reflectivity, close to that of gold, and because the surface is a liquid, it is self-healing. So we solve one of the issues for plasma sources, which is debris. Okay, normal incidence optics. The reason normal incidence optics were developed, like I said, is because at normal incidence, most materials don't reflect almost any EUV at 100 EVs. Molybdenum silicon multilayer mirrors were developed, and these give you extremely high reflectivity, but the limitation for use in metrology sources is this is only of use if you can get the mirror close enough to your light source to collect a sufficient amount of the photons and keep it clean, because they're very sensitive to damage. So I suppose a key message from the collection point of view of plasma sources is that you collect far more, you collect almost the same amount of photons in the first 30 degrees of emission as you do in the last 5 degrees. So higher collection solar angles are important to get to, but it's not so easy to get there and maintain high reflectivity. So a question I had to break the proceedings up a little bit was if the sun, if looking at the sun, directly at the sun on a bright sunny summer day in Ireland, which doesn't happen very often, if you have about 3 milliwatts in your pupil, what's the brightness of the sun? How would you go about working that out? So maybe I can leave you to work that out a little bit later on. So I'll come back to you after coffee, maybe I can ask you that question.
So 3 milliwatt is
the power on your pupil.
Power on the pupil.
Yeah.
Okay.
What's how bright is the sun? So it's interesting to work out that number in terms of EUV sources, because if Carl Zeiss had the sun, for example, as a light source, and if it was emitting EUV, it probably wouldn't be bright enough. So that's the challenge that we're faced with. So that's something about brightness and collection. Object illumination is the next thing I'm going to talk about, and again, I'm just going to introduce it. So we were talking before about small objects, and small objects being imaged onto a CCD. So the CCD has a size of 25 by 25 millimeters, something like that. You need a magnification of about 1,000 to see anything in small detail on the CCD, because of Nyquist limitations. So if you've got a 25 millimeter squared image here and you have 1,000 magnification, it means that your object field is about 25 microns. And with a 25 micron object field, if you were to start with a 25 micron light source, 25 micron diameter light source, you could see that with the high numerical aperture, the high collection solid angle here in your objective, you need to match that with your illumination. And with 1-to-1 magnification approximately here, you could image your light source onto your field of view, onto your object field. So a quantity that's conserved in optical systems is L2, which is approximately the area of the object, or the area. In this case, it's the area of the object of the lens system multiplied by the solid angle of the lens. So, for example, your object here has dimensions of about 25 microns squared, and your system and your object up here has dimensions of 25 millimeters squared. So the L2 conservation means that your solid angle has to be lower by that quantity, so that the two are reciprocally related. And it means that you need to. It means that, for instance, if you were to start with a large source here, and I'll go into this a little bit more later, if you start with a large source here of 500 microns, and you wanted to image that, and you wanted to use that to image in a system like this, then in order to match your numerical aperture here, and in order to match the area size of your object, you need to demagnify your source by a factor of, if it's a 500 micron source, you need to demagnify your source by a factor of 20, which means that you need to have a solid angle of collection which is 400 times smaller. So you lose 400 times of the light with respect to with respect to a smaller source. I'll leave that a bit more. So again, illumination is limited. Illumination solid angles are limited in most of the systems that we look at, and illumination object fields are limited in all of them. In the beam system, for example, the light source the photons have to be fed through a small solid angle because the objective of the beam itself geometrically limits how light can be fed onto the sample. So you have to feed through a very small pencil beam. You have to feed a beam of photons that focus onto an area, a usable area of a few microns, and that's extremely challenging. So, in metrology systems for EUV masks, the challenges are even bigger because their concerns in EUV metrology are to try and measure mask defects, and to do that accurately and to do that consistently accurately, they need to have extremely tight tolerances on all of the imaging parameters. So they take the light source, which we struggle so hard to produce photons from, and they remove 95% of the photons before they start with field stop, and then probably remove another 90% of the photons with a pupil stop to illuminate their mask to give them the best possible resolution and the most consistent resolution. And then they pass it through another 5 mirrors, which means that their total mirror throughput is approximately 2%. So they take 5% of 5% of 2% of the photons that we produce, and that's what they use in the imaging. So that makes our lives a little bit difficult.
Can you please explain that again?
So, in order to have uniform illumination on the mask here, if we produce a light source with a more or less Gaussian output, and if the illumination that they require at the surface is the illumination uniformity for imaging at the surface that they require is, let's say, 5%, or a few percent, then the metrology system manufacturers like Carl Zeiss, for example, can't use the photons that are further out in our Gaussian source. They need to take a section of the source which is sufficiently uniform to allow them to illuminate the object uniformly. So they chop the top of the source off, and they only use the part of the source that is sufficiently uniform, the brightest part of the source that's sufficiently uniform for them to illuminate the field that they're trying to image. And the fact that they use faceting like this for the illumination as well is down to matching the illumination conditions in the scanner, which is what they try to do with these metrology systems. And so they need to facet the illumination as well to match the illumination in the scanner, and that throws away even more photons. So it's a very lossy system. And then you have to produce a magnification of 1,000 on top of that again, so that spreads your photons out even further on your detector. So there are very high requirements for source brightness for that reason. And the solid angle of illumination here is limited in these systems as well, which means that you need to start with a small source to begin with. I'll go into that in a second. So if there was no illumination solid angle limitation, and if you were trying to illuminate the top of the screen rod here, if you're trying to illuminate something small with a light source which is large with respect to the thing that you're trying to illuminate, you can collect a large fraction of the light source, and in the collection process, in collecting a large amount of it, you can do either two things. You can either image the source one-to-one onto your object, in which case you will possibly fall outside the illumination solid angle, or if you have a restricted illumination solid angle, you need to magnify your source. And if you have to magnify your source, then you throw away most of the photons. If you demagnify your source to match the spatial size of the object that you're trying to illuminate, then you throw away most of the photons because you never collect them in the first place. So you have a choice of either collecting a lot of photons and throwing them away from a magnified source, or collecting fewer photons and passing them through the optical system. So in a rough sense, that's the choices that you have. And that's limited by the illumination angle of the system that you have as well. So if you have to illuminate to a specific solid angle, that restricts the amount of light that you can collect from larger sources as well. From a metrology point of view, the ideal thing to do with a fixed illumination solid angle or a fixed illumination auto-undo, is to use a small source or a smaller source and magnify it into the optical system. The collection fraction from your light source goes up with theta squared. So you're collecting more photons. If you collect more photons, then you need a smaller light source to begin with, and the power goes down with the source diameter squared. So you have a quadratic dependence of source size with power. So smaller laser plasma sources that you can magnify onto your object allow you to get the same radiance through the system. For example, again going back to our discharge plasma source of 350 microns, it's got a radiance of 10 watts per millimeter squared steradian. This is a 13.5 nanometer light source, an EUV light source, and the conversion efficiency of input power into these 13.5 nanometer photons is approximately 0.5%. So you need 2 kilowatts of input power into this plasma to produce that 10 watts of output power, which gives you a radiance of about 10 watts per millimeter squared steradian. If you wanted to get the brightness required for metrology applications, which is over 100 watts per millimeter squared steradian, you need a 20 kilowatt input power in your plasma. That's not really practical in a small scale metrology system. So if you use a 20 micron source, a 20 micron laser plasma source, the power output from your plasma can be 350 times less or thereabouts for the same radiance. So you can transfer as much through the system with a light source with a power of 350 times less. So that's the illumination side of things. And where does UCD fit into all of this? We produce UV light sources, and this is what we're going to be working on with Drone, is producing small light sources that we can couple easily into the object field at the right numerical aperture for illumination of an EUV metrology system. And the source has to be small, and it's got tight wavelength requirements. And this is something that we work on in UCD. So we work on spectroscopy of sources, and more recently we're working on imaging of sources at small scales now as well. So previously, what we would have done to characterize our sources, we would use the CCD camera to look at a source, and we would use the pinhole as an imaging technique. And the limitations of this are that the airy disk from any point on your plasma is emitting over this radius, over this diameter, and the airy ring diameter from each of these points is approximately, or the angle of it is approximately 1.22 lambda over d. If you work that out for real numbers for what you're likely to be looking at, if you have 100 micron plasma and a pinhole which is approximately 10 centimeters from the plasma of 25 micron diameter, these would be typical numbers that we would use. Your at 13.5 nanometer radiation, your airy ring extends into 65 microradians, and if you just look at geometrically, if you look at this angle here, this total angle is about 62 microradians as well. So it means that your pinhole is your pinhole image is limited by the diffraction through the pinhole. So at about 100 microns of plasma size, the pinhole stops being useful as an imaging technique. So with Larissa last summer, we developed a normal incidence imaging system in UCD to image our plasmas. And the resolution that we want to get is somewhere around a micron, because we're looking at sources that are probably a few tens of microns in size. So we want to be able to, we would ideally like to get down to imaging resolutions of about a micron. So if we look at the Rayleigh resolution relationship, it relates the numerical aperture of your imaging optic and the wavelength of the light that you're trying to image, and the ratio of them will give you the resolution of the system. So if we know that we want to resolve about a micron at 13.5 nanometers, we know what the resolution is, we know what the wavelength is, and the numerical aperture works out to be somewhere around 0.007. So that means that if we have a mirror that's approximately 10 centimeters from our plasma, then we need a mirror aperture of about 1.4 millimeters. And the reason that's important is because we need to be able to put a small normal incidence mirror relatively close to a plasma that's producing a lot of debris as well as a lot of radiation, and we can achieve 10 by imaging in a system if we start off with a spherical optic with a focal length of maybe, I can't remember what it was, 75 millimeters or something like that. So that's the system that we developed for measuring sources. So source size and source radiance are important. Source size and source power. The size tells you the radiance when you know what the power is, and we need to be able to measure that in the lab. And this is the system that we developed. We've modified that system slightly since, so now we can use the system to look directly at different types of plasma systems where we haven't got easy geometric access, and we use 2 multi-layer reflectors to do that. Only one of them is curved. In the other part of characterization of the light sources that's important is spectroscopic characterization, and the considerations in soft X-ray spectroscopy are similar to the considerations in imaging. You need to use grazing incidence optics in spectroscopy because the optics can't they must function over wide wavelength ranges. You need to use back-thin CCDs or phosphors and multi-channel plates, and we've also got time resolved systems now that depend on multi-channel plates and phosphors as well. The systems that we have in UCD are we have a broadband soft X-ray spectrometer which works between 1 and 20 nanometers. It's a flat field instrument, and flat field it has a quarter meter. It's a quarter meter system, so the dispersion is over a quarter of a meter, and one of the gratings works between 1 and 7 nanometers, the other one works between 5 and 20 nanometers. We can exchange the two without breaking vacuum, and this is very useful. So we have a broad survey instrument in this, and this will be useful in the work in Karuma's work in the PhD. And we have higher resolution systems as well, but this is a very useful broad survey too. Absolute measurements we make with a similar system that was developed in Aachen, and it's got a more restricted wavelength range between 8 and 17 nanometers or something like that, but it works exactly the same. You've got a flat field grating, and the flat field grating just works by having the grating spacing set, the variable grating spacing set in such a way that the dispersion field is flat over a region large enough for a CCD to collect the spectrum. So if you had an evenly spaced grating system here, then you would produce your dispersion over a Rowland circle, which will be difficult to couple a CCD to, and that's why flat field imaging systems were developed. So we have these in UCD, that's what we use. We have broader VUV characterization systems. We have a 1 meter normal incidence system that works between about 30 and 250 nanometers. And we have Cherney Turners, and both of these systems have recently been fitted with electronic detection. We have a cross Cherney Turner system which allows us to look at the vacuum ultraviolet as well. And the vacuum ultraviolet is going to be important in Garum's project because we're going to be able to use it to look at plasma temperatures and plasma densities, hopefully, by looking at line widths and line heights. Time resolved, we have recently acquired a Hamamatsu camera which has a gate time of down to 250 picoseconds, and we worked on producing phosphors that are able to respond to this type of time. So we have PTV phosphors that have a rise and fall time of about a nanosecond now, and we're working on zinc oxide, doped zinc oxide phosphors which have faster responses too. But we've got some initial results from this in spectroscopy and imaging using these phosphor systems on tin and gadolinium. So just in summary, the name of the group is the Atomic, Molecular and Plasma Physics Group. And the range of things that we do, it's commonly known as spec lab, and what we do is spectroscopy, and the range of spectroscopic diagnostics that we have, it covers from the X-ray all the way up to the infrared. And these tools can all be deployed in the projects that we're undertaking. So the project at UCD and the PhD project that Garum will undertake will be to try and develop a high brightness source. And the idea is to use a low energy electrical discharge and couple a low energy laser into the discharge after it's been formed in order to take advantage of the relative low cost of producing a low energy discharge system and the cheaper cost of producing low energy laser pulses to produce a bright light source. The group that he's going to be working with are there are about 10 staff and about 10 students at the moment. The numbers change, but that's approximately the scale it's been for the past 4 years or so. And you've met some of these already. The system that Garum will work on is it's not particularly well drawn here, but we've got two rotating liquid electrodes here across a power supply, across a capacitor bank, and a laser plasma is produced, or ablation is produced by an initial laser pulse, and that ablation, like I was saying before, gives you a conduction path between the electrodes, and that's where your plasma is produced. And what we want to do in the project with Garum is to focus a CO2 or YAG laser into the plasma after it's been produced, to produce a region of the plasma that's got so we start off with a plasma that's about 10 eV, which is relatively easy to produce. We need to get the right density to match the CO2 or YAG laser coming through, and the idea is to try and couple the laser into a sufficiently small volume that we can get a high brightness light source from this in a simpler way than just using a powerful laser or just using a more powerful discharge. So the discharges are typically limited in size and can't scale up in power, and lasers are typically expensive at the high powers that would allow you to make a metrology system. So we try to use the advantages of both to produce a discharge system. The lasers that we're going to use are a CO2 laser with 1 joule in 50 nanoseconds. We have shortening techniques that can take that down to 2 nanoseconds, but we lose most of the energy. It goes down to about 30 millijoules. But we may end up using the shortening system. We also need to improve the focusing of the laser, because currently we can only focus it down to about 200 microns, 500 microns. Okay, 4. Okay, so we need to improve that. So, well, we can start with the CO2 laser, and that's what we'll do. We have one of the reasons for using the CO2 laser in the system as well, like I said before, the critical density for a CO2 laser is about 10 to the 19 centimeter per centimeter cubed, which is something we should be able to achieve in the discharge, which should allow us to couple the CO2 laser effectively into the discharge over a small length scale. And the other advantage is that the UV opacity at this density is quite low. So we should be able to get our UV photons back out through the system again as well. the other lasers that we have we have a selection of YAG lasers, which we're going to be able to couple into the system as well. And most of these YAG lasers are much higher beam quality, so we're able to focus them down and produce plasmas of the order of 15 microns in size. We have an ultra-fast terawatt laser system, but I won't go into that, it doesn't work at the moment. So early, I had a wrap-up slide, but I never got to finish it. So to wrap up, I suppose I could probably talk a little bit about some of the stuff that's gone on in UCD, or some of the measurements, some of the types of measurements that we've done. And typically, using our absolutely calibrated spectrometer, we're able to produce spectra between about 8 and about 18 nanometers, something like that. And Laura Morris was able to look at the angular emission characteristics of our laser plasmas, for example, and to look at how absorption at different angles from the normal to the surface, how absorption varies, and that tells us a little bit about the characteristics of plasma at different angles, and that you've got lower ion stages. That lower ion stages predominate in the laser plasma at higher angles from the normal. And again, looking at angular, we was able to look at angular emission and see the effects of emission angle on on the output photons, on the total photon output. So this is important for collection purposes, for an EEV system, for an EEV source. And looking at out of band again, as I was saying, the mirror systems tend to be able to reflect the out of band radiation very effectively. So to come up with a way of quantifying and reducing out of band radiation that's harmful on the system, we were able to do that as well. I haven't got a very extensive list of the results that we have produced, but essentially the group's been working on target dilution, on emission from various angles, and we've been recently working on newer materials, on gadolinium and other materials for 6.x lithography, if that was ever to come to pass. That's more or less where we are. That's about it.
I was just wondering, when you're going through about going to the CO2 metrology, are you looking at going down to UV lasers, kind of frequency tripping, because then you get smaller spot size and smaller emission volume.
But it'll be higher density. So
yeah, but it's just kind of again part of the trade-off between brightness and source size. That you should be able to get smaller source with a shorter wavelength laser because of better focusing and higher density. The emission becomes smaller.
You could, but you won't necessarily get a smaller plasma just because you've got better focusing. So the plasma expansion is, let's say it's 10 to the 7 centimeters per second. That's 100 microns per nanosecond.
Yeah, but the emission volume should be smaller, the same way you have a bigger emission volume for CO2 than the eye.
But the emission isn't going to come maybe from the dense region. The emission that you see is going to come from outer regions in the plasma. No? Yeah, I don't know the answer, but yeah, I mean, we haven't gone into it, but that's something we should start to look at. All right, yeah.
What was the question?
Instead of for metrology, instead of going to longer wavelength lasers, going to short wavelength lasers.
In order to focus better. But the problem is it goes through the plasma without interaction, really, because the interaction length it's reciprocal fragments.
Not really just on
So he's not talking about in the hybrid system. He's talking about just in general. If you're just focusing onto a solid material. So.
Yes, that's also there is happening.
Yeah, no, I was just wondering, like this, in terms of the trade-off between, you should have smaller source, but not as bright. In terms of the trade-off between...
So a lower conversion efficiency with a smaller volume, or smaller size.
In terms of what you're looking for, which is more important, reasonable brightness with a big emission point or a small emission point with a worse brightness.
I suppose it depends on the system you're using, and some numerical aperture limited systems like the Carl Zeiss AIM system, the power requirements aren't particularly high, for example. But in other systems, you have larger autolu in the system, and you still need fairly large powers. So power is an important feature as well as brightness. I didn't really go into that too much. But yeah, there is a balance between all that. So that's something we should probably look at again. Thanks for that.
Can I try to give the answer to the question?
For the sun question?
Yeah.
Yeah, good.
So maybe it's with power, let's say 3 micron. 3 microwatts.
3 milliwatts onto
3 milliwatts.
onto your people.
Yeah, 3 milliwatts divided by the area, 6.5. 6.5 square. Area of the retina.
The area of the retina is about it's about 2 millimeter diameter or something like that. Yeah, maybe a bit more. Not the area of the retina, the area of the pupil.
Okay.
So
So the scar of it would be level 2R, I think 2 pi.
The solid angle that your eye subtends, the area so it's the area of your eye divided by the radius of the sun, more or less.
Okay.
So you can work out the solid angle that your eye subtends at the sun, and then work out what the total emission from the sun is. And then if you work out what the radius of the sun is, you can work out what the brightness of the sun is using that. And it just so happens if you work out the numbers, the brightness of the sun is about 2 watts per millimeter squared to radian, which is a lot. So I don't think my numbers are on there, but that's it. Anyway, that's it. Thank you.